Hi there, and welcome to Graphing Part 2. In this video, we're going to talk about scientific notation. So our key ideas are: how do scientists handle very large and very small numbers? And how can you tell the precision of a measurement? So to answer our first question, how to handle very large and very small numbers, to reduce the number of zeros in a very big and very small numbers, we express these values as simple numbers multiplied by a power of 10. And this is called scientific notation. So scientific notation is defined as a method of expressing a quantity as a number multiplied by 10 to an appropriate power. So I'll show you some examples of this here in a minute. But let me give you some more information first. So some powers of 10 and their decimal equivalents are shown below. So 10 to the third is 1,000, 10 squared is 100, 10 to the first is 10, 10 to the 0 is 1, and actually any number to the 0 power is 1. 10 to the negative 1 is 0.1, 10 to the negative 2 is 0.01, and then 10 to the negative 3 is 0.001. We can use scientific notation to make calculations. So when you use scientific notation in calculations, you follow these math rules for the power of 10. So when you multiply two values in scientific notation, those exponents or power of 10 are going to add. And then when you divide, you subtract those power of 10. So what I want to do on this slide is kind of go over what scientific notation looks like, a couple of rules, and then show a multiplication and division example of scientific notation. I'm going to use some pretty basic, simple math here, but when you write scientific notation, so let's start with some big number. Let's say we've got 23,500. Sorry, that's our number. It's a little bit bigger, and what I want to do is I want to show this number without these extra zeros. So what I'm going to do is I'm going to place my decimal point in there, so I'm going to pretend like that decimal's there. I'm going to then move my decimal over to where it's between the 2 and the 3. So this first number, when I write scientific notation, can only be a number between 1 and 9. So it can't be 0, it can't be 10. So when I rewrite this number then, so this 23,500 number, I'm now going to write it as 2.35, and with scientific notation I'm going to say times 10, and then I'm going to count how many places I moved the decimal over. So I went 1, 2, 3, 4. Because this number, 23,500, is bigger than 1, my exponent is positive, and I moved it 4 places. So this is the number of places I moved my decimal. I don't need to write a plus sign to indicate that it's positive, so it's assumed to be positive when I write it like such. Alright, let's look at a really small number now. So let's say I've got 0.00235. So again, I can only have a number between 1 and 9 in front. Notice my number is really small. It's smaller than 1 because there's not a value here. So again, I'm going to do the same thing. So I'm going to move my decimal over until I've got the first number as a value between 1 and 9. Alright, so it's 0.000235. 1, 2, 3, 4. So this is the same as writing 2.35 times 10. Because this number was smaller than 1, these 4 places that I moved over, again, I'm still going to have an exponent of 4, but I'm at a negative 4 because this first number was smaller than 1. So let's look at multiplying and dividing these numbers really quick. So 2.0 times 10 to the 4th, and I'm multiplying that, so I'm going to put these in parentheses to indicate that I'm multiplying two numbers. Let's say 3.0 times 10 to the 4th as well. I'm going to close my parentheses to show that I'm multiplying these two numbers together. So you're going to look at your sign, it's multiplication, so you're going to multiply our two bigger numbers. 2 times 3 is 6. 6.0. I put times 10 in here still, but since this is a multiplication, I'm going to add those exponents. So 4 plus 4 gives me 8. So 2.0 times 10 to the 4th times 3.0 times 10 to the 4th equals 6.0 times 10 to the 8th. Alright, dividing 4.0 times 10 to the 8th. I'm going to go ahead and put these in brackets, but I'm going to put a divide sign in here. So I can either put a slash or I can put the symbol for division. And again, I'm going to make these really easy for me. So I've got 2.0 times 10 to the second. So I have 4 divided by 2. So I got 2.0 times 10, and then 8 minus 2, so times 10 to the 6th. So we've got a couple of examples here when writing scientific notation. We pretty well kind of went over this already, but the adult human heart pumps about 18,000 liters of blood each day. So write this value in scientific notation. So you can list your given and unknown. So I know the volume is 18,000 liters, but I want to write it in scientific notation. So I want some number times 10 to some exponent. So what I can do is I can either move my decimal or I can divide. So what you can do is find the largest power of 10 that will divide into the known value and leave one digit before the decimal point. So you get 1.8 if you divide 10,000 into 18,000 liters. So 18,000 liters can be written as 1.8 times 10,000. Then I write 10,000 as the power of 10, so it's 10 to the 4th. So 18,000 liters can be written as 1.8 times 10 to the 4th liters. Personally, I think it's much easier to move the decimal. So your decimal is here. Count over to where you've got one number, 1 through 9, as your first number. So I've got 1.8 times 10 to the 1, 2, 3, 4th, which is exactly what they got. Here's a problem that's presented here. Your county plans to buy a rectangular tract of land measuring 5.36 times 10 to the 3rd meters by 1.38 times 10 to the 4th meters to establish a nature preserve. So what's the area of this tract in square meters? So we're going to list our given and unknown values. So we're given the length is 1.38 times 10 to the 4th meters. Our width is 5.36 times 10 to the third meters. And we want to know area. So we can find area by multiplying length times width. So you take 1.38 times 10 to the fourth meters times 5.36 times 10 to the third meters. And what you can then do is regroup if you would like to, but basically you're multiplying 1.38 times 5.36, and since this is a multiplication problem, you're going to add those exponents. So you're going to add those powers of 10. So multiply and add, we end up with 7.3968 times 10 to the 7th meters squared. And then sometimes we could round up too, so we could round to 7.40 times 10 to the 7th meters squared. Alright, so how can you tell the precision of a measurement? So scientists use significant figures to show the precision of a measured quantity, and precision is the exactness of a measurement. So a significant figure is a prescribed decimal place that determines the amount of rounding off to be done based on the precision of the measurement. So if we go back to the previous example, our given values had 3 significant figures. So this is a measured value, 1.38. 5.36 is a measured value, and they are both 3 significant figures, so we have 3 numbers there. So when we get 7.3968, we're going to want to show 3 significant figures. So when we go out to our third significant place, we've got a 9, and the next number is a 6, so the 9 rounds up to a 0, which rounds the 3 up to a 4, so that's why we get 7.4 on the previous example. And then we can talk about accuracy too. So precision and accuracy are different. So accuracy is a description of how close a measurement is to the true value of the quantity measured. So let's take a game example here. So we've got a pen, and we're throwing these little circles, these little hoops to the pen. So when we get these hoops on the pen, we have good accuracy because we're near the post or pen, and we have good precision because all the hoops are close together. On B, we've got good accuracy, so we're near the post, but we don't have good, we have poor precision because they're spread apart. So again, good accuracy, good precision because they're together. On B, we have good accuracy because they're near the post, but poor precision because they're spread out. And then we can look at the other 2 examples here. We have poor accuracy, but good precision. So poor accuracy, they're far from the post. We have good precision because they're close together. And then on this last example in D, we have poor accuracy because they're far from the post, and poor precision because they're spread out from each other. So we apply this to graphing by looking at our data points when we start graphing them and seeing how close they are to the expected value. So that's all in this video.